Okay, everyone, I have 1 o'clock, so let's go ahead and get started. I want to thank you all for coming to our now virtual event, Agriculture and Water Quality, how do TMDLs and edge of field monitoring fit in, with our guest speakers, Greg LaBarge and Josh Griffin, and I will introduce them in just a moment. You should be seeing a poll question right now. That's just our regular data that we request at every event, just so we can get a better understanding of who our audience is and who we're reaching. So if you wouldn't mind filling that out, I'd really appreciate it. And we'll move along here with a couple of housekeeping things before our presentations. So today's schedule, as I mentioned in the flyer, we are offering CCA credits for soil and water management, and those will be offered at the end of today's event, towards the end of Q&A. So first off, we'll have Greg LaBarge, and his topic is Infield Practices to Reduce Nitrogen and Phosphorus Losses, followed by Josh Griffin, and his topic is Ohio's TMDL process and the Mommy Watershed Nutrient TMDL. And then we'll have a panel type discussion with questions for both speakers at the same time, and I will be moderating that. So a few notes before we get started with today's event. This event is being recorded, and the video will be posted to the Ohio State Agronomy YouTube page, hopefully under the Water Quality channel. And if you registered, you will get an automatic email with the link to the recording after it has been posted. There is a Q&A box at the bottom of your screen. You can see it pictured here to the right. If you have questions for either speaker, please put those in there. And if you would prefer to verbally ask a question, go ahead and raise your hand and we'll give you talking privileges during Q&A. And if you experience any technical difficulties, you can use the chat box to ask questions of our hosts and panelists, and someone will try and help you out. So without further ado, today's speakers, Greg LaBarge, first off. He is a professor and Agronomic Systems Field Specialist here at The Ohio State University. Greg's extension and research emphasis is on nutrient and water quality impacts from row crop production systems. His focus is specifically on nitrogen and phosphorus management effects on crop yield and water quality at the edge of field. So with that, I will turn it over to Greg.
All right, Rachel, are we seeing the presenter
Yep.
mode?
Yep, it looks good, Greg.
Perfect. Yeah, good afternoon. Appreciate the opportunity to talk a little bit about agronomy and then how that relates to nutrient loss and management that we need to be doing on our farms. Josh is going to cover the TMDL, which kind of sets a target as far as different expectations of loading coming out of different watersheds. And the way we approach it from trying to reach those targets from an agricultural perspective is to think about infield practices and how they impact the water quality leaving our farm fields. We're going to talk about a few practices today that are really general practices that can be applied to any field that will in particular relate to our phosphorus management. Then we will also talk about some other practices that are more infrastructure, require a change in either field topography by actually placement of different practices within a field. And those are really going to be field specific and based off of a need within those fields that we identify. So a couple different ways that we need to go about this and give good thought to what we do from a management perspective. When we think about what we impact from an agricultural perspective in today's current water quality scenarios, it's really thinking about three things. It's thinking about erosion, it's thinking about nitrogen, and it's thinking about phosphorus. And really, when you start talking about the nutrient side of the three that I just mentioned, really they interact with that erosion loss. So we need to be thinking about all of those really simultaneously. So let's jump into it. And we're going to talk for just a second about erosion, just to keep it on your mind. And what we really need to be thinking about is infield erosion. We've got in the upper left-hand corner here we've got a infield where we have erosion coming across, cutting a gully through that field. So thinking about a practice there to stop that erosion is good and maybe useful from a water quality perspective, and also from a management of the field perspective. Running equipment across those gullies can be either damage the equipment or worse, break something that actually we have to go out and repair in the field. Then thinking about it from a outside of the field perspective, but still very important, is the streams, a large network of ditches and streams that drain Northwest Ohio. A number of miles of this bank area that we need to be concerned about, and looking at stream bank erosion is important. And we really do also need to keep in mind how weather events have affected us from an erosion perspective. The picture down here at the bottom is a field situation this spring where we had basically 9 inches of soil that moved to the edge of the field. It was related to some tillage that went on in a really no-till cover crop system. But even in that system, with some spot tillage to correct some issues that were out in the field, we exposed that soil to loss. So always being conscious as far as where water is moving from within our fields to the edge of field is important, because as we think of and look at some of the satellite imagery from Lake Erie, you can see here an early season issue that is presented very clearly as far as the sediment entering Lake Erie in that satellite image. And when we think about water moving downstream with sediment in it, any place it slows down, whatever's heavier than the water is going to carry based off the current volume is going to fall out. And that in particular happens there at the Toledo Harbor, where we have dredging that occurs, but it can also occur upstream and impact fish and wildlife habitat as we have sedimentation occurring. So just some things to keep in mind. And, there are a few practices that we know work from a erosion control standpoint, certainly in field, thinking about reducing tillage, no-till situation. Cover crops are really an important tool for us in relationship to erosion loss. And then we can think about some of the gully areas, depending on the topography in the field, it may make sense to put in some vegetative filtering or buffering practices, like a grass waterway that we see shown here. Those are very effective. When we think about this sediment moving downfield, in particular, it carries phosphorus that is bound on that sediment particle moving downstream and adds to the phosphorus load. In a few cases, it may impact nitrogen because we can also have ammonium on the soil particle that's moving downstream and can disassociate as well. So really keeping erosion and doing the things that we need to do to solve or reduce the amount of soil loss from our farm fields is still a good practice, and we need to be thinking about how we get that accomplished. Let's talk for a few minutes about phosphorus. And really, when we think about phosphorus management, it really goes back to a good soil test is really essential from an agronomic perspective, and we use that on a frequent basis. But it's also a very useful starting point for us when we think about environmental risk. And you see either a 0 to 8 inch or 0 to 6 inch sample, that agronomic sample taken in a good representative fashion across the field really is important for us as a management tool. And the reason it fits in so well for us is that we know from a yield perspective how that affects yield. We know that at the critical level defined in our tri-state fertilizer recommendations are 20 parts per million phosphorus. As long as we're above that, we really don't see any change in yield based off of seeing an increase in soil test level. We know that if we rely only on the soil test level and we're below that critical level, we can actually and let me back up for just a second more clearly to state that if we're below the critical level of 20 parts per million and we rely only on the soil test phosphorus available to the crop from that shown in that soil test for crop yield, we know that we're going to have a high risk of yield loss. And you can see how that's expressed here as far as a percent of yield reduction. We mitigate that. In other words, we prevent any yield loss by using fertilizer when we're below that critical level, and those annual applications in that range are a good agronomic practice for us to think about. We can use the soil test level also to discuss how much loss of phosphorus we can see at the edge of field. What you see here is a representation in the blue line as we have the soil test level increasing, and we have our DRP concentration of water coming off the field on the second y-axis here. We see that concentration slowly go up as it increases, and then we actually reach an inflection point where we see an increasing rate of loss based off of a higher amount of soluble phosphorus in the soil system. And this is some numbers that was actually done from some research just to the north of the lake in Ontario, showing losses and how that relates to soil test level. And it's really right around this 113, 120 part per million soil test level that we see at concentrations increase. When we talk about Lake Erie, our target of water going into the Western Basin to reach the goals of a cleaner lake is to have that DRP concentration be 0.05. So we can see down here in this agronomic range that we have, water quality does hover right around that 0.05 or less. It's when we start to get above that that we start to see the losses of DRP increase. And then at some of these higher soil test levels that we see have a much higher amount of DRP leaving the field. We can kind of divide this up into, 4 risk categories, one of those being low, and we're less than 50 parts per million. Then we can talk about moderate, high, and very high, depending on where we're at on that soil test level scale. So going back to that soil test analysis, taking a look at that, we can get agronomic information, and then we can also get field specific information as far as risk of phosphorus loss as one indicator. So we can use that soil test P as a screening tool. Here we have soils from different fields and different levels. And if we take a look at it and kind of put it into that risk pattern, we have really 2 fields that were have a high risk and we want to be concerned about first, and that is field 5 and field 6, where we're above that 120 part per million. And we want to understand what the loss is of those from those fields. We know that really when we talk about these high fields, not everybody has in particular fields, and that would be an entire 20, 40 acre field that's at these soil test levels. Often what we have is we have zones within the field that are at that level. And this is a distribution of different soil test levels. It's some information that TFI provides, and we can take a look at over time changes. And we have 4 different reporting periods, 2005, 2010, 2015, and 2020 here. And we can see that we do have a high amount of our soil tests that fall into that less than critical range of 20 parts per million when we think about row crop production. And in fact, that's increased over time, the amount of soil tests that fall into that category. This is kind of that maintenance range where we want to keep soils in, kind of that good agronomic range where we don't need to rely on annual fertilizer applications for maximum yield. And we can see that's declined. And then we start to get into these higher risk fields, and we can see that highest risk where we're above 200 parts per million, really it's a fairly low quantity of the soils that come in. And once again, often those high soil test levels are only sections or areas of a field and not an entire field. One thing that I think we need to tout more is that actually from a fertilizer standpoint, utilization standpoint, we are using less fertilizer in the state of Ohio and also up in the Western Lake Erie Basin. And you can see here once again, TFI type of data that they summarize from a commercial fertilizer standpoint. And then I've also added in orange some ODA data that I have access to. They tied together and give us an idea of fertilizer use. And actually what we see is that since 2006, basically what we see is the declining rate in fertilizer usage, and that declining rate here in the state of Ohio is about 1,000 tons per year is what the trend line shows. When we talk about that from a nutrient balance perspective, in other words, how much phosphorus are we putting into the system? And this would be phosphorus from fertilizer and manure here in the state of Ohio versus what we're taking off in crop yield. What we see is we do have a negative balance. We're actually pulling down soil test level, or excuse me, we're using more phosphorus than we're putting into the system with our applications of manure and fertilizer. So when we go back to this view of soil test levels, that really explains that we're using less than what we're taking off, or adding less than what we're taking off of P fertilizer. That explains these trends that we see where we actually see declines in soil test levels. And from a perspective of water quality and this impact of soil test level on what we see as far as DRP leaving a site, what we basically have is a good story to tell from an agricultural perspective. And while it's going to take some time still to pull down those highest soil testing fields, it is a way that we're headed in the right direction. So when we talk about phosphorus management, let's talk for a couple minutes here about that agronomic range where we have our lowest potential risk of DRP loss. And really what we want to do is manage based off of the tri-state fertilizer recommendations, where we use the critical level from an agronomic perspective, and then we use this maintenance limit from an environmental perspective, where we have, depending on our rotation, either 40 or 50 part per million soil test P levels. When we're above that, that's when we need to think about risk of loss. When we're below that, we have some things that are good in the system. We don't have a lot of excess P, so we have really a less risk of loss from a DRP perspective. So we want to get that good soil test, and there's some things here in relationship to just some good management practices that we want to implement to define a field and then collect that soil sample on a regular basis. The thing that we want to do in then fertilizer application is a few things that help lower our risk even more when we make that application, is to not use any more than a 2-year rate of P. We don't want to leave that nutrient on the surface. So when it's on the surface, we have the potential for water to move that nutrient. It's not going to be a critical loss in that we're going to lose 100% of the phosphorus, the fertilizer that we put down, but we will lose anywhere from 1 to 5% of the nutrient that we apply, and that loss can occur by surface flow directly into a conveying stream or ditch. We can lose it down through preferential flow to the tile lines, or we can also have it surface drain, or where surface drains exist, that phosphorus flow and end up into the stream system. Any of these tend to give us a higher loss with that fertilizer application and any rainfall event we immediately have after. That's why the rules in place as far as precipitation and managing application timing are really critical and good things from a water quality perspective. This field situation where we're less than 50 parts per million, that's also the place where from a livestock manure management standpoint, we want to put those nutrients to give us the best agronomic benefit. Let's focus a little bit on the high side and what we need to think about as far as practices there. And really, when we talk about being just above that 50 part per million to maybe around 120 part, that kind of lower increase in DRP that we see in the water quality data, what we want to do is, well, first and foremost, there's no economic return to adding commercial fertilizer with that type of soil test, so we can suspend any commercial P applications. Manure use, we want to can use manure in those situations, but want to use manures that are at a rate that it's not going to continue to increase that soil test phosphorus. And in fact, we'd really like to lower the soil test phosphorus, particularly if we're approaching that 120 part per million. And the best way to do that is, once again, to identify lower soil testing fields to target with organic matter or organic nutrient applications. In these fields, continue to soil test because, first of all, we're managing a lot of other nutrients with the soil test. And then secondarily, we want to see that change or trend over time and see what's happening to soil test levels so that we know where we potentially need to change management. And finally, we can do some things within crop management. We can, using practices that are good agronomically, that maximize yield, is a good water quality practice for us to use, because the more nutrients that we take off in the crop, the less we have exposed that's going to be potentially lost downstream. Then we can also consider different crop rotations. Forages within a crop rotation really do positively impact somewhat phosphorus, but for sure nitrogen when we talk about management. When we get into those higher or highest ranges, we really start to think about maybe pulling a grab sample from flow tile or tile flow that's coming off of those sites. Gives us an idea, are we actually seeing coming out the end of the tile some of the higher soil test or DRP amounts coming off? And if that DRP amount is greater than 0.2 parts per million, that's where we can start to consider some of the practices we're going to talk about in a minute, as far as more infrastructure type of practices. Manure use, really in these situations, we want to find a different field to go to with manure application. Like we indicated earlier, continuing to soil test for other nutrients and then monitor that change in time. And then the practices that start to decrease soil test level by maximizing yield or crop rotation changes are important with these soil types as well. The reason that we really need to look at these higher soil test fields or areas of fields differently is it's going to take a long time for us to change soil test level. Here we have different starting levels of soil test phosphorus. This is some work out of Maryland. We have 50, 125, 200, and you see the trend here. And you can see over time we have a 400 part per million soil test. And even after 18 years, we're still at a 300 part per million soil test. So those high soil tests, take advantage of them, mine that nutrient out of the soil, reduce your fertilizer costs, and you have really generational type of soil test levels when you're at 300-400 parts per million before you need to make any additions. And so because that's going to be a long-term change to get soil test levels in an area where DRP is going to be reduced by just having adjusted the soil test level, it makes sense in these fields to think about some of these infrastructure practices that are going to need to be in place, and when they're in place for a long extended period of time will be effective as far as reducing phosphorus. So kind of going back to that discussion here of some of the other practices, and really it becomes water management in those high soil test fields. Certainly building soil health, and I think of soil health, they're equated to soil organic matter. If we can increase organic matter through tillage, crop rotation, cover crops, doing other things that will combine in that system to improve the biological, chemical, and physical properties of the soil. That's a great thing, particularly if we can increase water holding capacity. We see less water leaving a site, and that less water leaving is leaving more nutrients, more of those soluble nutrients in particular, there right on the site. Vegetative filter buffers, and you see all the different options that are there listed. Really, those do work for us to filter water, remove sediments and the nutrients that are attached to those sediments, and is a good practice to have where we have concentrated flows of water leaving a site. Those high soil test fields really are ideal to think about a phosphorus removal structure. That's where we put a structure in place with a media in it that actually captures the phosphorus. When we talk about those, they're very effective, reducing by 16 to 71% the amount of DRP concentration that would be in particular in the water that is actually running through the filter. With some of these higher flows, we actually have to divert some of the water around the flow or around the filter in order to get drainage, which is our main reason for having those tile systems in place. Some newer discussion revolves around drainage water recycling, where we actually take a portion of the field, capture the water, and then irrigate back out into the field for times where we have low rainfall, and in particular those July, August periods where we're going to have a great impact on yield. By having a closed system, we don't see any nutrients leaving the site. Constructive wetlands are another place that we can have an impact in relationship to the amount of phosphorus leaving, total phosphorus, DRP, as long as we have some retention time within that, can be impacted. So constructive wetlands are certainly a choice for us to think about. The benefits there are, thinking about, wildlife and some of those kind of habitats versus the previous practice we were talking about where we're actually capturing the water and potentially irrigating it back on the field. Just some general comments on these practices. They're generally best suited for those higher P-loss sites. If you have a very low loss, the ideal of spending the amount of money that it might take, and depending on the practice here, we're talking about $1,500 to maybe $20,000 to put a practice in place. And so spending that money in places where we have minimal loss really doesn't make sense from an economic standpoint, and if we want to solve the problem. We also may have some maintenance issues or costs associated with these, particularly when we talk about that P filter. We may need to either renew that, or some of the media are actually rechargeable. In other words, we can leach out the material that's captured in that using a product, and then recapture that as it is leaving, and either put it back on the field, or in some cases it may be just a better, in other words, in some cases we have phosphorus that is actually totally bound to the material and it's not going to release at any point. And the discussion there is maybe use that for driveways and as a gravel type of replacement. With some of these practices, I mean, you can see a wetland, you can see a retention structure for water is going to take land out of production. We can talk about a P removal filter, and actually we can kind of conform that to maybe a border area where we really don't impact production. So there are ways to make these infrastructure water management practices work. A couple of other practices that I want to mention, and that is a blind inlet is one where we have surface water that flows to a standpipe, what we see existing here in this field on the left-hand side. We put in this media with a pipe system that the water filters down through, and then the water goes out. We could even think about replacing this media with a steel slat. In this case, it's gravel. We could replace the gravel with some of the pea retention type of materials. And rather than the standpipe in the field, now we have this area that we can drive over and don't have to worry about equipment. We can reduce sediment load by 79% and total pea loads by 78% in those types of structures. Drainage water management, there's a lot of these structures in Northwest Ohio where we change the water table. It can be a very effective practice for us from a nitrogen perspective. From a phosphorus perspective, it's really going to depend on how that structure gets managed and how much water we have as that managed or in raised water table, how much precipitation we have when it's in that raised position. If we increase the amount of surface water that leaves the site, actually we can see it negate any benefit of reducing P coming through the tile line. So there's some management things that we need to figure out with water control structures. We're gonna switch focus here to nitrogen for a couple minutes and kind of finish up here. Really, when we talk about nitrogen, it's a rate discussion, and that rate discussion for us here as far as corn management in the state of Ohio starts with a MRTN rate that we get out of the corn nitrogen rate calculator. We have 200 plus, actually it's approaching 300 different experiments that go into that rate calculation. We determine the yield response, and then we identify on that yield response curve where it makes the most sense based off of current corn and nitrogen prices to make our nitrogen rate decision. Good place to start. There are some other things that we can consider in making a nitrogen rate. And in particular, that occurs with manure. The things that we need to consider with manure is, what is the ammonia content of the manure tests where we're making an application manure. That gives us a place to understand how it compares to commercial fertilizer. That's really critical if we're top dressing wheat so that we don't have the wheat go down. It's also important to understand when we're in a corn crop and using that to replace the nitrogen that we might apply from a commercial fertilizer standpoint, to understand that we're getting enough units of nitrogen down, and that really that nitrogen rate when we're considering ammonia can be the MRTN rate when we're making that decision. The amount of nitrogen available from a manure perspective is really contingent on two things. It's placement. If we surface apply versus subsurface apply, it's going to make a difference. Surface applications, we're going to see volatilization losses, and we will see losses of nitrogen that aren't crop available and can cause issues, in fact, lower yields because of that loss from the surface application. Timing. The further away we're making this manure application from when a corn crop in particular is going to take it up, if we're doing summer right now for a corn crop in 2023, nitrogen is going to be lost. If we're doing a fall application, early fall, we can see high losses. If we're getting to the point where soil temperatures are less than 50 degrees, we can see losses decrease. Spring application, we're closer to crop uptake, so we can rely on more of that nitrogen. And then certainly an in-crop application, we can take full advantage of the nitrogen to replace. When we're in that summer, fall, spring type of application timing, a pre-sidedress nitrogen test is really something that we can use to make nitrogen decisions for our corn, or really our cereal grain crops in general. The reason we want to think about rate and timing in relationship to nitrogen is we see that as rate increases and yields decrease, and that yield decreasing is often because of weather conditions during the growing season, that we see higher amounts of nitrogen left in the soil. This is some plots that we have at Northwest Ag Research Station. We've been doing some rate trials there for a number of years. In the past few years, we've been taking fall or end of the season soil nitrogen test. And what we have is, here's our rates that we apply as far as starter plus side dress, ranging from 0 up to 250. And then what we have here is the pounds of N that's in the soil in both the nitrate and ammonia form. And what you see is we can draw trend lines through those yield or through those years and those different rates of nitrogen, and see that with an increasing rate, we have increasing residual nitrogen in the soil. In 2016, we have the highest amounts, and at our 250 rate, actually a 240 pound rate, we have really left over almost 165, 170 pounds of nitrogen at the end of the growing season. 2016 was where we had yields of, at the agronomic optimum nitrogen rate of 157. So a dry year. We can look at here 2020, another year where we have, in this case, around 90 to 100 pounds of residual at the end of the season. Another year where we have yields being lowered because of weather conditions. Then in a good growing season like what we have in 18 and 21 here, we can see where those residuals, even at that highest nitrogen rate, is 50, maybe 30 to 50 is what we're talking about as far as residual. I'm talking about pounds of nitrogen. Pound of nitrogen today, we can kind of talk about in relationship to $1 a pound. So, we're talking dollars per acre that are there, and how do we take advantage of that nitrogen that's available? Just back up to this slide. This is another experiment. Here we have that pounds of nitrogen in the soil, and we have different soil sampling times: June, November, March, and May of the following year. And what you see is the pounds of nitrogen going down. What's happening to those pounds of nitrogen can be kind of indicated by what we see in our edge of field studies here in Ohio. And basically what we see is that nitrogen being lost out through the tile system. We have these basically 20 sites with 2 fields located at each site. And you should get excited about a couple of these where our average from 2011 to 2020 is nearly 100 pounds of nitrogen coming out through the tile system. And this would be nitrate nitrogen being lost out through the tile system, represented by that dark area of the bar. So really, costly under current nitrogen price situations. So how do we save some of that nitrogen? What do we need to do to prevent those dollars from going downstream? And really, the ideal of cover crops to retain excess nitrogen is really a prime opportunity for us. This shows a seasonal change, and I won't bore you with the numbers, but basically you have a cover crop here, and the amount expressed in pounds per acre over here on a monthly basis as far as loss. And here in December, we have a much lower rate of loss per pound per acre of nitrogen with a cover crop versus no cover crop. You see that trend really happening throughout all of that fall growing season and into basically corn planting the next year. That cover crop giving us advantage, taking up nitrogen, reducing the amount lost through tile. Here in Ohio, our edge of field studies, we show an average reduction of 39 pounds per acre. We see an average of 84% reduction in the amount of nitrate loss. Pretty good success there. And if we're talking about 160 pounds of nitrogen and we're able to save 84%, that should translate into a lot of material to go back into the soil system from an organic matter perspective. And cover crops, we do know, help us from a soil health parameter perspective. What you have here is some results from some sampling that appears in our eFields research bulletin, and you have organic matter across the bottom here. You have a change in scaling here, And basically what you see is that where we have no cover crop, which is the orange, the average amount of organic matter falls in this 2.5% or 60, almost 70% fall in that range, versus shifting the curve to closer to 3% where we have, yes, cover crops in the system. You'll see that same thing from an active organic matter standpoint, measured as a POX test. Not quite as pronounced, but is there from a respiration or amount of biological activity within the soil profile. So cover crops, improving soil health, and making a difference from really a nutrient cycling standpoint, as well as the other benefits that we see of increasing organic matter. When we talk about other practices beyond just thinking about cover crops to capture nitrogen, and I ought to back up 1 second. We were talking about manure earlier, and if we're applying manure this time of year to a wheat stubble field, and we maybe we're putting out 200 to 250 pounds of nitrogen in a 6,000 gallon swine manure application, that nitrogen is going to be lost unless we do put a cover crop in there. We may be able to retain a little bit, but it's going to be a fairly minimal amount. So really any time we're applying manure, summer, early fall, getting a cover crop in place to capture that nitrogen just makes sense. If we get into some of the other things that we can do from a nitrogen perspective outside of managing rate and using cover crops to capture any residual nitrogen, then we get into these water filtering and control practices. We can talk about a wood chip bioreactor, and they are very effective, 15 to 60% reduction of the water that flows through those particular structures. Reality is there's a cost there, and there is no way to regain that cost like potentially we can from increasing cover crops, or through cover crops increasing soil health. Drainage control structures work really fairly well by reducing the amount of water leaving a site from a nitrogen perspective, and we see reductions of 22 pounds per acre in some of the literature and studies that have occurred there. So drainage water structures, while they're a little bit iffy from a P perspective, are really good from a nitrogen perspective. We can use saturated buffers. They're very effective, and that's where we basically take that field grass buffer area along the field and run a tile system parallel to that, and then the water is pumped back into that tile system and it flows through the grassed area, and that would be below ground or subsurface, and flows and enters the stream here. And after going through that filter, very effective, 30 to 85% reduction in nitrogen from water that's diverted through that practice. Once again, we've got management of boards, and we, under high flow conditions, may see a lot of bypass of that filter. So just some things there that, while they're effective, it's costly to put in place, and maybe doing rate and cover crops makes more sense. I'm not going to go through this slide other than to make you aware of it. We were talking about some of these practices and individual effects earlier here in the presentation. This is out of the 4R Plus program in Iowa and their nutrient reduction strategy, and they've gone through some of the different literature and studies out there, and come up with the changes in load reduction from a nitrogen and a phosphorus standpoint from putting those practices in place. So you can start to do some comparison of different practices that you might think about for your farm and what might fit your field. So just kind of finishing up here, manage erosion is still critical, and we want to do that from a sediment standpoint, and the sediment reduction also keeps some of the sediment bound nutrients in place. Use for our nitrogen management for P and nitrogen. One thing that often people think about is discounting the nutrients that are in manure compared to commercial fertilizer. And the discount would only come from the ideal of spreading and whether we're getting an even spread out there. But basically, if you look on a manure test and you look on a commercial fertilizer bag and you see, 40 pounds of ammonium nitrate, that ammonium nitrate doesn't change form and it isn't any less effective from a crop production standpoint when it's in manure compared to commercial fertilizer, given the caveat that we're getting or doing a good job of spreading that. And then some of the conservation practices, which really start talking about managing water, are important. Soil health, and I equate that once again to soil organic matter. Doing those practices, while it's hard to find that benefit from an economic standpoint in the cropping system short term, we need to start looking or thinking about long term and how it might impact your farming operation. And then as you're looking at soil tests, we'll soon be in the prime time for soil sampling and then reviewing those soil samples to make decisions, whether it's this fall or next spring. Identify those areas where you have high soil tests and particularly soil tests that are above 120. I could even argue back to 50 parts per million, and think about how and what you can do to either reduce the soil test level, or maybe more importantly, think about, is this a field where filtering practices make sense to reduce the impact of that high phosphorus area within a field. Just a few useful references are tri-state fertilizer recommendations. There is a good publication that some of the nutrient loss criteria that we talked about, assessing nutrient loss risk in Ohio from NRCS, that's available. We do have our Ohio Ag BMP handbook, which really goes through and talks about pros and cons and where to find resources on some of these different conservation practices. And then we do have a fact sheet out there that kind of goes through that soil test decision-making tree from both a yield perspective as well as a reducing P loss at edge of field standpoint. And with that, we'll turn things back over to Rachel.
Thank you so much, Greg. That was really informative. And if anyone has any questions for Greg, please go ahead and put those in the Q&A box. And I'll let Josh have the floor here in just a minute. But Josh is the Lake Erie Programs Manager for Ohio EPA, and he is in the Division of Surface Water. Josh coordinates between divisions programs that play a role in managing Lake Erie's water quality and serves as the project lead for the Maumee Watershed Nutrient TMDL. Josh started with Ohio EPA in 2012 and spent time in several programs in the Division of Surface Water, starting in water quality assessment and modeling program, and then in permitting programs. So with that, I will turn it over to Josh, and we'll follow with Q&A.
All right, I'm gonna go ahead and try to share my screen here. Can you all see my screen?
Yep, it looks great.
Okay. I can't see the meeting controls now, but everything popped up, but we'll just go with it. So I think you can see my screen, and I think as I was listening to Greg, it was always hard to follow. Yes, I always learn something when I listen to Greg. I hope you all can learn something from me today too. But I kind of, my thought was, we're really talking about two kind of extreme scales of thinking about water quality. And with TMDLs, we're thinking about, this large, and especially with most of what I've been doing lately is working on this Maumee Watershed nutrient TMDL project, which is what I'm going to focus on with some kind of more general information about TMDLs in general. So this like really big scale of thinking about water quality down to what Greg talked about is this like really how do you make change happen at the field scale on the landscape, and I think how we can tie the two together really helps think about how you can effectively manage water quality at this much larger scale by thinking through how and why we got to where we are today and what we could do to make a difference. So hopefully we can draw that connection today. So I'm going to kind of start out generally talking about what is a TMDL and kind of Ohio's TMDL process, and then go through an overview of a recent report we put out for the Maumee River Watershed Nutrient TMDL called the Preliminary Modeling Results. I'm going to focus on a couple of key areas within that report that kind of hits on the things that we have to do at this stage in TMDL development. So, you know, Ohio EPA, we developed TMDLs for surface water that's not meeting a given goal for that, for a water body and for a specific pollutant. And the TMDL determines the maximum amount of that pollutant that we can deliver and still meet those water quality goals. So we're often looking for a reduction from some existing condition to some target condition in the future. And within the TMDL, we allocate the pollutants to different sources. So the non-point sources, agriculture, stormwater, other sources from the landscape that are generally not regulated under the Clean Water Act, and also the point sources that are regulated through the Clean Water Act. So they get some different considerations within the TMDL, but we allocate load to all of those different sources of a given pollutant. And then we also make recommendations for implementation. Some of those recommendations are for implementing the waste load allocation, or for the point sources are things that we do implement directly through our NPDES permitting program. Implementation actions of a non-point source are recommendations and planning type actions. And ultimately, we have kind of a continual process of assessment, evaluation, development, and then kind of after you start implementing the strategy, you kind of move through that again. You continue to evaluate the situation, and then you adapt your implementation as new information becomes available. So TMDLs and really water quality planning is really this kind of iterative process that we work through with time to make continual progress. And so with that kind of in mind, there's a little bit of, TMDLs do some specific things, but they don't do other things. And it's important to kind of keep that in mind as you think about developing a TMDL and what you might see in an implementation plan. So, we have these TMDLs. Ultimately, they are planning tools that we use to allocate pollutants to those different sources. They do establish those waste load allocations I mentioned. Those are implemented in our NPDES permits. So from a point source perspective, a wastewater treatment plant perspective, the load allocation is something that is ultimately permitted to in their permit, and they monitor and meet a waste load allocation in their permit. Then they provide some technical details that we can use at the local level to develop non-point source pollution reduction implementation plans. This type of watershed planning, something that's been done for a long time. Currently, it's our 9-element non-point source implementation strategies. That's kind of the specific vehicle that we're using for that local planning component. So going from Maumee watershed down to the local 12-digit HUC scale, which is around 20 to 30 square miles. So the TMDLs they do encompass both that point and non-point source component, and there's a plan to achieve the loads for both. But ultimately, the TMDLs don't change policy or legal authority of any implementing agency. So the implementation plan is something that's done kind of consistent with our authority to facilitate implementation on the non-point source side and implement allocations and NPDES permits on the point source side. With the Maumee watershed TMDL, it's a little bit different project than what we typically do. Most of our TMDLs in Ohio to date have been evaluating, the impacts of sources on nearby water bodies. So say we evaluated the Blanchard River and we found a portion of the stream that wasn't meeting water quality standards, we would develop a TMDL and allocations and a plan to improve water quality from those nearby sources to a nearby impairment. But here with Lake Erie, we have a large watershed that contributes phosphorus to Lake Erie and the Maumee. And those impairments in Lake Erie are driving the planning efforts for sources that are really quite far away from the actual impairment, especially if you follow the streams as they flow from Lake Erie through Fort Wayne and on down to St. Mary's, Ohio, is a lot of river miles, and that far field aspect of this TMDL is something that we haven't often done in Ohio. So it's something a little different for us, but ultimately we're addressing impairments in Lake Erie with sources of phosphorus throughout the Maumee watershed. So to put the TMDL in context of all of the other things that we're doing in the Maumee watershed in Northwest Ohio and the Western Basin in general, the TMDL is really, another piece of the pie. We're still using the same reduction goals that come from Annex 4 that have been used for planning for Ohio's Domestic Action Plan and H2 Ohio. That means we have to achieve around that 601 metric tons, and this is Maumee Basin wide. So this includes some loads out of state. The TMDL does bifurcate loads coming from Indiana, Michigan, and Ohio. Our plan is specific for the Ohio component of the watershed. And as we develop the TMDL, our rules for Ohio EPA require us to take some additional considerations to support some of the management choices associated with the economics and equity between different sources, what's been done to date, and what would be most cost effective for implementation. So there's a host of other things that we are kind of obligated to do that kind of bring some formality into the planning process once we're developing a TMDL and thinking about implementation through that lens beyond the existing implementation work that's ongoing in the Western Basin. And as we develop these TMDLs in Ohio, some of those requirements are now that we follow a 5-step process, and at each step in this process, there are opportunities for public engagement. So we start with a study plan. There's a biological or water quality report. Then and those things are kind of setting the stage for identifying the impairment. And what really kicks off TMDL development and loading analysis planning is this load analysis plan, then a preliminary modeling results report, and an official draft TMDL. That official draft TMDL, after we put it out for comment and stuff in Ohio, we then submit to US EPA Region 5, and they review and approve that TMDL. So to take that process back to where we're at with the Maumee River watershed, we published the final loading analysis plan in January of this year. We developed the PMR. We got that completed and published at the end of June. We started out with a 30-day comment period. We got some requests to extend that, so we've now taken that out to August 17th. So there's opportunity to comment on that document still. I believe the fact sheet for that document is posted as a handout. So if you're interested in reviewing it or anything, that opportunity still exists for a couple of more weeks. That is an intermediate step, so there's still opportunity to revisit and talk about and evaluate anything in the PMR through the final TMDL, which we're targeting to get out at the end of the year. Another opportunity for public comment on it. That one is required to be at least 60 days. So there's a 2-month comment period there. And we're going to have some additional outreach to kind of talk about the comments we got on the PMR as we finalize it, and give some updates at least one more time between now and publishing the final TMDL. There's also most likely going to be a hearing or additional in-person outreach during the draft comment period. So lots of opportunities to get involved and comment and learn more about the TMDL for the Maumee River watershed that we're working on right now. So, with that kind of TMDL background, I want to take some time to kind of focus specifically on what's in the Maumee PMR right now. This kind of where we're at in the TMDL development process. One of the big things we put a lot of time and effort into in this at this stage in the TMDL is just kind of looking at what's there. Where is phosphorus coming from in the Maumee watershed? And how we got to where we are today, and also those specific sources. So I'm going to talk a little bit about what's in that part of the report. So we start out by looking at trends and watershed loading as it stands today. And one of the recent publications, this is, I still say recent, it was published last year, as a little bit of a different way of looking at phosphorus loading in the watershed. And this is focusing on the loading point that we've been monitoring. Heidelberg University has been monitoring for the last 40 years now. So looking at how phosphorus and dissolved reactive phosphorus have been changing at that location over years using a newer technique called flow normalization. So we kind of take some of that year-to-year variability out of it to create this smooth trend line that you can see with the open dots that kind of smooth out the scatter plots in each of these plots. And we see this fairly continuous decrease, slight but nonetheless decrease in total phosphorus that's happened over this period of record over the last 40 years. But in that same time frame, we've seen the dissolved reactive phosphorus be somewhat dynamic, and we've seen concentrations decrease, stay fairly flat through the 1990s, increase again up into the early 2000s, and stay fairly level since then. So we know that the main thing that's changing in the watershed that's fueling these blooms out in Lake Erie is this dynamic trend in dissolved reactive phosphorus. And Ohio EPA, to kind of start thinking about where phosphorus is coming from, this is something we do statewide for our nutrient mass balance report, is since 2016, we've been publishing that nutrient mass balance study and kind of coarsely breaking down where phosphorus is coming from in different watersheds across the state. And in the Maumee, from that, we've seen that, by and large, phosphorus is from non-point sources. Point sources contribute at a lower level. And then we've also put the effort into evaluating the role of the household sewage treatment systems, HSTS, playing a smaller role yet, but nonetheless a source. phosphorus in the watershed. And one of the things to note is, the point sources and HSTS, they kind of contribute at a fairly steady rate from year to year through time. But from year to year, we see big fluctuations in the non-point source contribution, largely driven by rainfall and stream discharge in a given year. Non-point source loads are very tightly linked to watershed hydrology and stream discharge. So within the source assessment, we try to dive down into where the sources of phosphorus are on the non-point source side, and we broke that into 4 categories: agricultural fertilizers, commercial fertilizer and manure, both specifically discussed within there. Sediment and legacy sources, so that erosion component and the phosphorus that's kind of accumulated in soils from prior nutrient application, be that from commercial fertilizer or manure. The role that streams and ditches play from erosion standpoint, and also what's happened with that watershed hydrology that maybe played a role in changing phosphorus. So it's all about understanding what's changed with these sources with time, and understanding that DRP trend being dynamic, and trying to add some value for planning purposes, that understanding how we got to where we are today, and what's causing the problem, that we can make more informed implementation choices. So Greg did a good job kind of covering here the how we manage phosphorus at a field scale. We included some discussion of that in the report. And we highlighted that tri-state standards were recently updated, and there were a couple of recommendations or a couple of changes in the tri-state standards that we would expect to continue to facilitate reductions in phosphorus applications in the watershed. A trend that Greg highlighted is something that we've seen with times, that we're actually applying less phosphorus in the watershed. And those 2 main changes is that we used to, in the recommendations, once you got above the maintenance limit, there was up until a certain point, there was a recommendation to continue to add some phosphorus every year. And now there's, when you're using commercial fertilizer, there's no recommendation anymore to continue to add any phosphorus once you exceed that maintenance limit. And the other is that, we've changed the calculation for how much crop removal is happening as we see a trend in phosphorus content in grain. So to raise 200 bushels of corn, you're going to recommend for replacement and maintenance, you're going to recommend less phosphorus as that's changed. So a couple of things that are just going to kind of work into the system with these new recommendations that should continue to move that total phosphorus application trend in the direction it's been going. We did do some additional analysis of manure sources of phosphorus, and we do see from the early 2000s to 2017 that we have increased livestock inventories in the Maumee River watershed, largely coming on the swine and poultry industry, but growth across the water, across all categories. This is normalized in animal units, so we can compare chickens and cows to that kind of same normalized value. So we kind of see this general increase around almost 80% increase in animal units in the watershed. But when you look out at a broader scale, we do see that this has happened in the last couple of decades in the context of a local minimum of livestock inventory in the watershed in the early 2000s. So we saw declining livestock inventories up until about the early 2000s, and then an increase in livestock inventories in the last 2 decades. At the same time, looking at some of the information Greg presented in fertilizer trends and crop removal, is that we see fertilizer or crop removal has increased. Our yields have increased over the last 15 to 20 years. And that trend goes way back. We've continued to increase yields for quite some time. But at the same time, we're applying less phosphorus. So we're increasing yields and applying less phosphorus. So kind of finally, to put all of those pieces together to try to kind of drive a point home on fertilizer, manure use, and crop removal, we combined and I say we worked with ODA quite a bit to do this analysis. They did the analysis. We've reported it in the TMDL documents, this preliminary modeling results report. So you put the fertilizer and the manure and the commercial fertilizer together, and you divide that by the crop removal based on the yield of corn and soybeans across the watershed for a given year. And we see this downward trend in that ratio, where 1-to-1 would say we're putting on the same amount of phosphorus as we're pouring out in a given year. And anything less than that would say that we are taking more phosphorus out in the crop than we're putting in fertilizer, be it from commercial fertilizer or manure. So seeing, from a water quality perspective and a phosphorus management perspective, a positive trend there, and that we are increasing our efficiency. We're drawing down phosphorus in the watershed. So good trends to see there. Some additional notes from literature review on agricultural fertilizers. From a variety of studies, we see that manure supplying around 20% of our crop need of phosphorus. And there's also a handful of studies that, when we're using manure effectively at agronomic rates, we have a similar impact for phosphorus loss from agricultural fields. So commercial fertilizer manure, when following DMPs, should have a similar impact on phosphorus loss at the edge of the field. We have multiple sources have pointed out that we have seen this increase in livestock population. So we are seeing a change in what source of phosphorus is being used for agricultural fertilizer in the watershed. So ODA and another analysis by EWG have shown that. I think some others have reported out that change has happened with time as well. So kind of our baseline for fertilizer sources, and it is dynamic. I think that's important to realize, because these aren't static things in time, that we do see these changes happening. So moving on to the agricultural soil and legacy sources of phosphorus. Historically, we have seen conservation practices reducing soil loss. NRCS has done a good job documenting this through the seep process and others. So we've seen pretty dramatic reductions in sediment loss. We also have to recognize that legacy P is one of those kind of terms that gets used to say a lot of different things. So in the most simple way, legacy P is just phosphorus that's accumulated in the soil from past applications and management. Sometimes people use legacy P to talk specifically about high soil test phosphorus. And sometimes people use legacy P just to talk about any phosphorus that wasn't part of an active application in the last so many months. So It's a term that has a lot of different meanings in the literature. It makes it a little bit challenging to, when you're leaning on that literature, to kind of define its role. But I think it's important to recognize that there's phosphorus in the soil. Sometimes phosphorus in the soil reaches higher thresholds that cause greater risk for loss. Greg did a good job covering that risk. And we've also seen some of these changes back to the reductions in soil loss. We've seen differences in how we manage tillage and water leaving fields, and there's been some interplay between those improvements and a change in how that dissolved phosphorus moves across the landscape. So I'm going to highlight one thing from this slide, in that I kind of covered some of these points when I was talking on the last slide. These changes in dissolved phosphorus, it wasn't the intent of soil conservation that we have an increase in dissolved phosphorus, but it wasn't wholly unpredicted, in that there were some people, even in the 1980s, as we were amping up our soil conservation efforts, that were saying, what we might see is not, yes, we'll see this reduction in sediment and total phosphorus, but at some point we might see that total phosphorus start to become increase in dissolved phosphorus, and we see kind of a change in those ratios, which is ultimately what we've seen in the Maumee watershed. So that soil conservation has played a role in how dissolved reactive phosphorus in particular moves through the watershed, and that there are trade-offs for managing different pollutants. But we don't want to diminish the value that we've gotten from that. So we've not only have we seen and measured the decrease in sediment loss, we've also physically measured water quality improvements due to those things, especially in our streams in Northwest Ohio. There have been multiple studies that documented reductions in sedimentation in stream channels and improvements in fish communities. And with Ohio EPA sampling programs, we've seen our pollution sensitive fish, especially those sensitive to nutrient or to sedimentation, dramatically increasing their distribution. And here's two of our good examples that are highlighted in a couple of our reports in the Auglaize, on surveys for the Auglaize and St. Joseph's and Tiffin rivers in particular, places we've surveyed in the last 10 years, where we see these sand darters, the fish on your left, and big-eyed chub, fish on the right, distribution increasing substantially throughout what was their historic range in the watershed. So great things happening there, showing the potential effects of soil conservation. So we don't want to say, oh, but now all we care about DRP. So we got to keep that push-pull relationship in mind as we look forward for nutrient management in the watershed. And I'm not going to go here. Greg did a better job talking about it than I will here anyhow. But again, as soil phosphorus increases, eventually there's that inflection point. This is not from the Ontario study. This was from a study in, I think, out in Kansas. So we see that same trend, this inflection point. Once you get above certain thresholds, you start to see more loss of dissolved reactive phosphorus. And this is getting at that high soil test phosphorus component of legacy P. So to kind of summarize, or to kind of draw from some other literature that's been published in the watershed, in 2019 was the year we had, kind of widespread preventive planning. We didn't see nearly as much phosphorus application in that springtime period. But we didn't see DRP decrease as much as fertilizer decreased. So it's kind of another line of evidence that a lot of the DRP we see, or a substantial amount of DRP we see, is stuff is from phosphorus that's already in the soil. It's not just going to be managed by these ongoing fertilizer applications. SWAP modeling work supports that and shows that, you know, the phosphorus that's already in the soil contributes around 18% of the DRP. That one reason that could potentially even be an under prediction is we don't have high soil test phosphorus represented to date in those SWAP models. So we're kind of assuming in those models that phosphorus is evenly distributed in soils across the landscape. So there's likely or potentially some underestimate there. And we have ongoing studies in that as well. We're trying to improve that component, and the proverbial we are working to improve that component. So there's a SWAP modeling project at Ohio State that's trying to, or that's going to put that distribution of soil phosphorus into the model as to improve that in the baseline model. And also looking at different ways how we can kind of identify and match best management practices to places where we do have high soil test phosphorus. And knowing those are high cost practices, making sure that we're getting them in the right locations through public-private partnerships. Both studies going on at Ohio State right now. So as much research as there's been, the research is going to continue. To get at those ditch and stream side sources, you know, we know from previous studies that we see streams as a source of phosphorus, especially total and sediment bound phosphorus. It covers a wide range across different studies, and that, you know, setbacks and conservation, the buffer strips do help reduce that stream bank erosion. So that's kind of what we glean from the literature. And also streams can enhance transport. So if we design our stream, as we design our traditional ag ditches, we want them to be stable. We don't want them to abrade excessively. So they're designed in such a fashion that they ultimately treat phosphorus less. And we can diminish our in-stream processes, and we often disconnect them from floodplains where phosphorus cycles through the landscape in a different way. So we kind of short circuit some of those natural functions of our streams. It's a consequence of our drainage infrastructure. Final point from the source assessment standpoint is that, you know, we have seen some fairly dramatic changes in watershed hydrology in this kind of time frame where we've been evaluating and managing phosphorus in the Maumee watershed. Rainfall on average has increased 12%, and that's led to a greater increase in stream flow. This mechanistically, you know, more high intensity events, more runoff during those events. So more water, 12% increase in precipitation leads to a greater increase in stream flow due to some of the other factors going on. This isn't spatially consistent across the watershed, and we've seen greater increases in precipitation and stream flow in the southern portions of the watershed. And again, that's largely with heavy and very heavy events. So less half-inch rainfalls, more 3-inch rainfalls. That's where a lot of it's coming from. because phosphorus loading and DRP loading are linked to the hydrology from the non-point source, more water, more potential to move nutrients off the landscape. This has implications for export. And so to try to look at this a little different way, we've seen Laura Johnson from Heidelberg often presents information from the gauges by kind of plotting the flow weighted mean or load and discharge. We know that discharge and load are heavily correlated. But if we look at the two different time frames here, where we've been monitoring at Waterville, so like the 1980s and 1990s, DRP load versus flow, and then the time period since the 2000s, there's a couple of things that are readily observed. One is that the relationship between flow and load has changed. The relationship is steeper. So there are some things that implies that there are things fundamentally different about the landscape that's changed the relationship between stream discharge and dissolved reactive phosphorus. So, that's kind of our landscape management, phosphorus management piece, and how DRP sources. But what really jumps out is that in the last 20 years, there are 5 years of rainfall or of discharge that exceeded anything that happened in the previous 20 years. So these are just very large flow years, and that has a big impact on phosphorus load. So managing water becomes one of those things that you kind of jump to when you think about nutrient management and water management and how they interact. So when you're getting a lot more wet weather, there's the potential for more load. And another thing that's been coming out of recently research is that how dissolved phosphorus moves through streams, the whole model and how we perceive that to happen is changing, and that phosphorus, we used to kind of think it just kind of moves through the stream channel, especially at high flows. But with some interaction in the sediment and floodplain potentially, but within the water column, it's largely just moving downstream. But recent studies have shown that there's actually a lot of interaction between dissolved reactive phosphorus in the water column and sediment in the water column, and that suspended sediment in the water column is absorbing phosphorus and changing that ratio as you move downstream. So less sediment in the water column increases DRP transport downstream. So it's another one of those interplays. Again, weighing those pros and cons of different management actions and how it influences pollutant movement and transport. There's always one more layer to the onion of complication, and this is one of those recent ones that emerged. Is in a way there's an ecosystem service from suspended sediment from a DRP management standpoint. We then go through, with the source assessment, we go through other sources of phosphorus, and kind of where on the point source side, that smaller sliver of the pie at the bottom of the watershed, within that, where does our phosphorus come from? And broadly kind of break that down into two categories for our wastewater treatment facilities, and then stormwater. Component of stormwater is a point source under the Clean Water Act. So I think very different discussions. Stormwater more hydrology driven. Wastewater treatment is that kind of continuous discharge into pipe wastewater treatment facility. So if we break down those treatment facilities, The Maumee, a chunk of it's outside of Ohio. It's roughly a 70-30 split area-wise. That's close to, the amount of wastewater that comes from inside of Ohio versus our adjacent states, Indiana and Michigan. We zoom in on that remaining 70% and try to look at what types of facilities that loading is coming from. And the biggest share of it comes from our largest municipal wastewater treatment facilities. Then our smaller municipal wastewater treatment facilities, and then a handful of industrial facilities that are generally have biological treatment. So there's some industrial facilities that contribute as well. But you can kind of see from a management standpoint, it's not size matters. So bigger facilities contribute more phosphorus. We also have our combined sewer overflows and bypasses that happen during wet weather. So some of our communities have combined sewers. When that plant's capacity is exceeded, some of that water is discharged in a untreated or undertreated way. But our estimates show that that's a fairly small component of the total phosphorus load. A lot of other reasons we're managing those discharges, but from a total phosphorus perspective, a small component of our overall loading. And then we wanted to put that community into the context of how they're performing today compared to what they would be authorized to do. I'm getting long-winded here on this stuff. This is the more exciting stuff that I have to talk about, is the source assessment. So, and generally we see that they overperform what they're permitted to do. And we've seen some general declines in recent years as facilities have further optimized their capacity to manage phosphorus, following generally the recognition that we needed to continue to manage phosphorus better in the basement. So those, we have ongoing optimization. We've added restrictions to phosphorus and laundry detergents and dishwasher detergents, and we have reduced those CSO discharges and bypasses. So all those things kind of work together to kind of continue to reduce phosphorus from that point source community. Stormwater, a lot of similarities between the other non-point sources, but some different forcing functions. Driven by hydrology. Another commonality is we've always focused on total phosphorus, and how this change in philosophy to kind of thinking about it and managing DRP as well. Overall, we don't have a lot of developed land in the Maumee watershed, Northwest Ohio in general. It's a small component of the landscape. But within that developed land, there's a couple of different management actions that you think through, and that impervious surfaces increase total discharge and transport efficiency of pollutants off of the landscape. And then you can also manage sources of phosphorus, which are different. We don't have as much phosphorus as fertilizer going onto the landscape. There's less than there used to be even, and we've seen a change in how lawn fertilizer formulations are reduce their dependence on phosphorus. We also can manage yard waste, leaf drop, things that put organic material onto our hardened surfaces. Pet waste and road grit also contribute to as sources of phosphorus, especially when they end up on those impervious surfaces and are readily transported. We have to bifurcate our household sewage treatment systems in the TMDL world into two categories. We have systems that discharge directly to streams, and we have on-site systems that use soil absorption. The on-site systems are part of our non-point source management. Discharging systems are covered by the Clean Water Act. We manage them as point sources. Within the something we also want to keep in mind when we're managing non-point source loads is that there is heterogeneity across the watershed, and some areas have higher pollutant delivery than others. And there's been a lot of different ways to try to slice that pie to come up with more efficient strategies to target areas that might be contributing higher. And that differs depending on whether or not you're trying to look at the watershed as a whole, or if you're trying to look at the field scale. So lots of different ways to slice it. And there's value. One of the things that SWOT modeling work in the watersheds told us is that there's value in trying to bifurcate those loads. Or trying to find those areas that have higher potential and to target them, because our BMPs will be more effective. We'll jump past the rest of that, but kind of or quickly point out that we have a large number of stream gauges in the watershed, and we, as we develop the TMDL, look to that network of gauges as another thing to evaluate, to look at where phosphorus is coming from in the watershed and how it moves. And one of the things that came out of that analysis is that similar to really that rainfall pattern, we see more phosphorus coming out of stream gauging stations. And this is if you look at kind of the distribution. The distribution rides a little bit higher in the southern part of the watershed than the northern part of the watershed. There's always exceptions to that, and some, so you see some gauges in the northern part of the watershed that are very high, and some in the southern part of the watershed that are very, very low. But if you kind of look at where that distribution lands, we see generally higher loading from the southern part of the watershed than the northern part of the watershed. So that kind of wraps up that source assessment. There's a lot of information in there. That ends up being somewhere between 60 and 80 pages of our report. So it's hard to kind of breeze through it quickly and efficiently. But it's one of those things that you got to set that foundation so you can effectively develop a model and then target implementation to the things that are going to make a difference. I'm not going to spend a lot of time talking about the model. To develop the TMDL, we're building on the mass balance type of model that we've used for first the nutrient mass balance study. Then in the domestic action plan in 2020, we used a mass balance model to develop some landscape targets that we've been using for far field planning and 9-element plans. And now here for the TMDL, we have to add a little bit more detail because we have to add some bifurcation for our stormwater that is regulated versus stormwater that is not regulated under the Clean Water Act, and for our household sewage treatment systems that discharge versus those that are dispersed on site. So we have to add a little bit of bifurcation for those loads. So we kind of built on the mass balance model, and the progression kind of continues. But ultimately, it's an empirical model that relies on loading information coming from that water bill 4 point that is, that big, important, continuous record that's taught us so much about what's changed in the watershed. And that's gives us that bifurcation then for the waste load allocation and the load allocation that are required for TMDL development. So non-point sources and point sources are further segregated for the TMDL than they were in previous efforts using the mass balance in the Maumee watershed. I'm not going to go through some of these details. These slides are largely from our presentations that are posted online. We had a stakeholder event back on July 14th. We're still working on getting that recording cleaned up, but you can get the longer, cleaner version of what I'm telling you today if you go catch that recording here. Hopefully in the next week we'll get it posted. So kind of skipping over some of that implementation stuff, or some of the allocation work to get to implementation, because that's really what it boils down to for non-point source management, agricultural planning is, we know that we have a reduction to achieve. It's largely going to be consistent with our ongoing efforts to plan for nutrient reductions, phosphorus, dissolved reactive phosphorus reduction in the Maumee River watershed. We're looking at it through a different lens now, and we're going to add some tools to our toolbox from the TMDL process. But ultimately, those tools don't change that much from a non-point source perspective. So right now, the TMDL, we're kind of laying out this strategy in, using our TMDL tools. That's the implementation plan that's going to become part of the TMDL. We have a framework for that in the preliminary modeling results report that we have published right now. And we've also laid out a framework for adaptive management, where we look at how we can track, monitor, and evaluate change in the watershed so that we can kind of continue to adjust the plan so that we make progress in the watershed. So this laying out clearly what that adaptive management process would look like is a big part of what we've included for implementation in the preliminary modeling results report. Developing that plan is that we've used that information from that source assessment to think about how and where we can get effective phosphorus reduction to happen. We have some reductions identified within the point source community. Something that we've continued to develop through H2 Ohio implementation in the state is to enhance these non-point source sinks. So as we've modified the landscape over the years to facilitate drainage, to try to reimagine that landscape in a way that we can continue to facilitate drainage, but also start to capture some of those natural functions to assimilate phosphorus and nutrients on the landscape and reduce their impact on downstream waters. Particularly helpful in a far field planning aspect, as we can place those practices anywhere within the watershed that they're most effective and have the desired impact on Lake Erie. But by and large, because so much of the load comes from non-point sources, a lot of the plan continues to be hitting on those same categories of how you manage nutrients in the landscape that Greg identified well. We have nutrient management, so on-field nutrient placement. I even think I stole that picture from the same place Greg did. Maybe I stole it from Greg. I'm not sure if it's his picture or not. I think it was. So we have ongoing erosion management, this ongoing a focus on water management and how we can reduce discharge and at least flow rates could be managed. and a lot of that water management is through emerging technology, some of the ideas of water reuse. This is a image of a cascading waterway. So how we can use these things that we've already set aside this land on, in part in the watershed to manage erosion. Are there ways that we could utilize it to manage water as well? So kind of looking at new ways to manage water and nutrients, knowing that we don't want to go backwards on the sediment management side, and we want to fold DRP into this phosphorus management more completely. I think we have till 3, so I have a few minutes. I can cover a couple of these last slides. I don't see a lot of questions, so I think I can take a couple more minutes. So for non-point sources, implementing a TMDL comes down to planning, and we have to make, within our argument, we have to demonstrate that we have reasonable assurances in place such that implementation is going to happen. And that largely happens through focusing on these initiatives and funding that facilitates implementation. So planning, our main planning tool that we, so through the source assessment, we identified those key areas, some key things that we need to consider for planning. Implementation needs to be widespread. DRP management is going to be more difficult than total phosphorus management. No single BMP is going to get us to where we want to go. So, a suite of BMPs, but also targeting those BMPs to the places where they're going to be most effective is important, and that we're going to have to consider things that we don't do today. We're going to have to continue to develop these emerging practices. The two primary planning mechanisms that we're going to continue to rely on is our domestic action plan and ongoing and improving our 9-element watershed plans. We have, I think, around 50 in the Maumee River watershed now. Ohio has 186 HUP 12. So we have both areas that we don't have plans developed for and areas where the plans could be improved or projects could be added to plans as funding and opportunities come into, are identified together. So we want to highlight within the TMDL is that, again, I mentioned this up front. I want to mention it again in the context of implementation, is that the TMDL doesn't give any additional authority over non-point sources, but we do know that policy changes happen and new regulations happen. We've seen both things happen. We've seen the nutrient management standards get updated. Those things are then often integrated into agencies, rules and policies that reference those as best science. So those kinds of things do happen. We've seen changes in regulations for managing manure, in particular on frozen and snow-covered ground in the watershed. So those new regulations do happen, even though the TMDL isn't the facilitating or driving force that says, you shall do anything. They do happen. So as we develop an implementation plan, it needs to be flexible enough so that as these policy changes happen, we can fold them into watershed implementation in a way that's consistent with the TMDL. And again, it comes down to state focus to these initiatives and how we get practices on the landscape. And these things go across all management levels. We have folks doing things voluntarily on the landscape. We have nonprofit organizations that bring citizens into the fold. We have citizens working at the local level and local government facilitating implementation. We have state and federal initiatives. So really it goes from the individual to the federal government. There's a lot going on in the Maumee watershed. And that's how we'll continue to facilitate implementation. And I talked a lot and I talked fast. When we did that presentation and covered this at our stakeholder meeting, I think we used about an hour and a half, and I think I did it in an hour. So I talked fast. We have a lot more information on our webpage. Links to that are in the fact sheet that was posted as a handout. You can always reach out to me or to our TMDL program if you have questions, thoughts about the TMDL development process, especially the Maumee River watershed nutrient TMDL. There's a lot going on with it right now. And with that, I can give it back over to Rachel, I think, to wrap us up if we didn't have any questions. I didn't see any.
All right, thank you, Josh. Let me just find my presentation, share it again. Okay. So now let's go ahead and move on to the Q&A session. Here in a minute or so, I'll flip over to the CCA credits side while we answer a few questions. So I guess we might as well start off with the big money question. So I think maybe both of you can speak to this a little bit, but how can we tie TMDLs and on-farm practices together to help improve water quality?
Okay, yeah, I'm unmuted. So, I think I hope you saw some commonalities between, how Greg was talking about on-farm management and how we're folding management practices into the discussion for this TMDL in particular. And I think that's, having a common language and a common recognition of the problem is a big hurdle to clear to start with, so that we have common planning objectives and recognition. I felt like I was almost repeating some of the things Greg was saying as I went through some of the considerations we're taking in the TMDL. So having that kind of collaboration so that we're speaking from a common language and a common baseline, I think is really important to link the edge of field to the far field. And the more planning that can happen at the local level, the better. So, with the TMDL, we can go as far as to facilitate planning from the watershed scale down to that 12-digit HUC scale. But at the end of the day, those implementation plans are only as effective as we get local engagement that helps us identify opportunities for implementation.
Yeah, I guess just to tack on to that, what Josh was saying, an important part of agriculture, or really non-point source measurements of impact at the end of a watershed, and you could use at any scale. You could use at the end of the HUC 12, or you can go all the way down to the Maumee. Reality is it's going to take a concentration of practice implementation. For one practice that we talk about in phosphorus management, subsurface placement, really the modeling shows that we need to be nearly 70% of the acres within a watershed from a non-point perspective implementing subsurface placement in order to attain goals. When we look at some research that talks about nitrogen management, cover crop adoption, getting up to that 65% adoption is where we start to see the water quality at the end of the watershed attaining goals. So it is because we have such a small amount coming from a very sparse or very general area that we need to really have those practice adoptions start to approach that type of level. The other, and in reality, we don't see as the one slide that Josh shared, water leaving my field in Paulding County does not stay in its same form as it enters Lake Erie at the end of the Maumee. Reality is it's transform and changes going downstream. So we need to keep that big picture in mind and understand that success is a joint success of many people adopting some of these practices that we're talking about.
Great. And speaking of that, what do you think the biggest barrier to adoption of some of these BMPs is?
Well, I think the barrier is always time and money, and the both of those. Well, and maybe an additional barrier is Mother Nature. I mean, we have a lot of people that are interested in cover crops and utilizing cover crops, but not every fall are we getting the opportunity to put those cover crops in. So, we need to be thinking about other options in relationship to, timing of putting those cover crops into the system. Can we do intercropping? Can we do aerial seeding more successfully with some other organisms added to the seed that kind of protect it? So, there are some things and technologies that we need to think about implementing, but time and money, and then how the weather conditions impact utilization of these BMPs are really three big ones, and a couple of those we're in control of, or at least we can start to maybe think about managing. Mother Nature is always the wild card. Great
response. I think a lot of that, I see a lot of that up here in Northwest Ohio, especially with our shorter growing season. One last question for Josh, and if you haven't already scanned for the CCA codes, go ahead and do that. But Josh, I wanted to ask you, does TMDL account for nutrient level fluctuations that are caused by these wetter years that we're seeing?
So the TMDL, we have, there's a component built into that, in that we're targeting, the 90th percentile condition. So we want 9 out of every 10 years to meet our goal, recognizing that some of the really, really wet years are just that, really, really wet. And we're, even with a high level of management, the water alone is going to push us past that objective, though we would still expect a dramatic improvement in Lake Erie's water quality in those years. It just might not meet the goal condition. So the wetter years are kind of baked into the target for the TMDL, I guess is the point of saying that. So
okay,
I would say yes. One word.
Good. Okay, so with that, I want to thank everyone that attended our event today. Thank both of our wonderful presenters. And you can see up on the screen here, we have email addresses for Greg, Josh, and myself. And again, if you registered for today's event, you should receive a recording once that's posted to the YouTube page. So with that, I'm going to stop recording.